Hey guys, it's Professor Chaserix here, and today we are going to be discussing an introduction to special relativity. Alright, so first I'm going to preface this by saying this theory essentially proves everything we thought we knew about motion is wrong. So, that's fun, right? Well, first let's do some history. Albert Einstein was the one who introduced this theory back in, I believe it was 1905, so early 1900s. And he said, hey, what if things that go really fast behave differently than what we perceive at our relatively low speeds? And essentially, the theory encapsulates describing relative motion in a completely different frame of reference, and we'll talk about that later, and how what we thought we knew about relative motion really is not accurate. So, a common example that shows kind of the absurdity of special relativity is, let's say we have Earth here, and we have a dude standing on Earth just hanging out, and then we have a spaceship, and I'm going to draw a box because I'm bad at drawing, and we have a guy in here, and he has let's say a meter stick. So he sees this as 1 meter long, right? Makes sense. He's moving at some speed v orbiting the Earth. We're going to assume it's linear motion. We'll talk about that later. But what we observe actually is this guy, we're going to call him Bob. When he looks up here, what he actually sees is, I'm just throwing a random number out there, but he sees a 1.5 meter stick, or a 2 meter, or just anything but a meter. And this phenomenon is really strange. Why in the world would he see anything but a meter stick? Well, it's because of the speed that spaceship is moving at. And that's what special relativity discusses. So, if you're here, I'm assuming you've heard of general relativity. So there's two pretty important distinctions. So let's talk about it. So special, this talks about space versus time, essentially. So it's going to discuss, it's going to discuss motion in inertial frames. This is extremely important when it comes to special relativity. So I'm going to circle this. So special relativity only works and only describes relative motion in an inertial frame, and we'll talk about that. Now, general relativity, is going to discuss a gravitational theory. Gravitational. I don't know if that's spelled right. Yep, okay. So, general relativity is much less about motion. Well, I guess it's technically about motion, but it's not about relative motion. It's actually about like celestial bodies and really, really large objects and how they behave, and warp space-time. So it deals with space-time continuum, and I'm sure you've heard of that, and that is also called the fabric of space-time. So these are two different theories. They slightly align because they're extrapolations on really big objects. So general is big objects in space. And special relativity is fast objects. So we're going to start off with special relativity because it is much, much less complex. So general relativity is extremely complex, and some of the equations just get completely out of hand, and general relativity is a year-long course in and of itself. So this is just a crash course to special relativity. So, what are inertial frames? I brought that up. It's extremely important. What is it? Well, an inertial frame, by definition, is a frame of reference. You know, I'm going to type this out and make it a little faster. Sorry, where's my keyboard? Come back, buddy. So, a frame of reference, I'm trying to think of how to word this, sorry, in which a body remains at rest if already at rest, and a body in motion moves at a constant speed in a straight line, obeying inertia. Okay, I think that makes sense. It's a little wordy, and let's discuss what that actually means. That's basically a dictionary definition. So, inertial frame. If I am standing on Earth again, this is Bob, right? Yeah, so this is Bob. Bob was born on Earth. He's never left Earth. He's never been on a spaceship to another planet. He hasn't been to Mars yet. So, in his mind, he's never moving, right? So, in our typical classical mechanics, Newtonian mechanics frame, we're just standing on a plane, not moving. We're not accounting for the rotation of the Earth below us, not the wind, nothing's moving. We don't account for the Earth moving in space. And then we don't account for the spin of the Milky Way, the movement of the galaxy, blah, blah, blah. So this is a good example of not technically an inertial frame, but a close enough approximation we can call it an inertial frame standing on Earth. Because the motion is relatively slow, because special relativity really only kicks in at super, super large speeds. And those speeds, well, this is referred to as a relativistic speed. So relativistic speeds are anything near the speed of light. And that's commonly denoted as c. Sorry, my parentheses look like c's. And this is approximately equal to 3 times 10 to the 8th meters per second. So super, super fast. Nothing, no physical object you can ever hold will ever go this fast, or even close to it. So this is when relativity kicks in, or special relativity rather, is super high speeds. Anything about a quarter of that speed, you can ignore when it comes to special relativity. The effects of special relativity are so negligible, you can just ignore it. So, first, let's talk about why Mr. Einstein here. Wow, that was not a good line. Mr. Einstein even proposed this idea of, because it's pretty absurd, and we'll talk about that. So he had two postulates. And a postulate's basically just like here's my paper, this is essentially what I'm proposing to be the nature of the universe, and the rest of the paper's based off of just these two postulates, and it always obeys these. So pretty simple. So the first one, number 1, is laws of physics. The laws of physics are always the same in an inertial reference frame. In any inertial reference frame. So this is pretty logical. In any frame that is inertial, you are always going to see the same physical laws applied the same way, doing the same things. So, for example, going back to this Earth inertial frame, if Bob is on Earth, whoop, hello Bob, welcome back. Earth is not Earth is technically accelerating because it's in circular motion, but we're going to just say it's linear motion right now. So Earth isn't actually accelerating at all. This means it's inertial. No acceleration, no change in speed, linear motion. Perfect example of an inertial reference frame. Enough. So Bob, when he drops a ball, so here's Bob's ball, it's going to fall at 9.8 meters per second. This obeys Newton's gravitational law, because the mass of the Earth is just going to pull the ball down, right? Makes sense. So if he now goes into, oh man, I can't draw an airplane, so this is going to be pretty bad. He goes into an airplane. And then he's moving at some speed v. And again, we're assuming it's linear motion, even though the plane's going around Earth, so it's circular. But he's moving at some speed v, and he drops the same ball. Well, guess what? It's going to fall at essentially the same rate, because the laws of physics are always the same. Simple example, but the most common example is like an elevator problem. So here is our building. Ooh, that's not a square or a rectangle. Here's our building. Then we have our elevator inside, and it's moving at some speed v. The important thing to denote here is it is inertial, which means that there is no acceleration. So a equals 0 all the time for inertial reference frames. If he drops a ball in here, guess what? It's actually gonna fall at the same rate, right? It's not gonna hit the ceiling because of inertia. The ball was already moving at this speed v. It's gonna fall at 9.8 meters per second because it's an inertial frame. So, laws of physics are always the same in an inertial frame. Done. Number 2 is kind of a mind-boggling postulate. It's completely absurd, doesn't make sense why this would ever be a physics law. Like, this sounds like it's out of sci-fi. You ready? Speed of light. So the speed of light is not relative. Wait a minute, I thought that was called relativity. Yeah. So, the speed of light is not relative. What does this mean? So, this is absolutely absurd when you really think about it. Let's say I'm in a rocket ship, which is just so happens to be a rectangle. And I'm moving at, let's call it 2.99 times 10 to the 8th meters per second. This is super, super close to the speed of light. That's a really bad 8. Super, super close to the speed of light. And now we have a little flashlight out here. Bing. And it's shooting off photons at the speed of light. So what one would assume is, and this flashlight's attached to the spaceship. So with Newtonian mechanics and classical mechanics, you would say this speed of the light would be the sum of, we're going to call this Vs, for speed of the spaceship, would be the sum of the speed of the spaceship plus the speed of light, which is c. But when you measure it, it's actually not the case, ever. It's never been shown to be relative. It's always just c. Wait a minute. So if I have a flashlight in a spaceship and I'm moving almost at the speed of light, how is that light gonna hit the wall in front of me in timely fashion? Well, it just does, because special relativity says it does. And we'll talk about length contractions and time dilation and stuff like that in future videos, which shows why this is the case. But this is weird, because if I'm moving, we're bringing Bob in here, he's our experiment. Let's say he's flying through space at 1.5 times 10 to the 8th meters per second, which is half of the speed of light. And then we have, so here's Bob. Then here's Bill. Oops. Sorry, Bill's a little mutilated. Bill is moving at the same speed. We're just going to call it c/2. If I have a stationary flashlight, not moving, here's my flashlight, and we're shooting it this way, and it's ejecting those photons at the speed of light, c. Well, Bill, as we just stated up here, he is going to measure c, which again doesn't make any sense at all, because we've always thought that speed is relative. But for photons, that's actually not the case, and partially for electrons, but that's a whole different video. But Bob, he's going against the speed of light, which is 3, right? So classically, you would say what Bob perceives those photons to be traveling at, if you were to measure them, he'd say the speed of those photons, we're going to call it P, is equal to the speed they're being ejected at minus the speed I'm going against them at, because of vector subtraction, right? So you would end up with a total relative speed of c/2. Again, that's not the case. What? How does that make sense? It really doesn't, but it's extremely complex, and that's what Einstein sought to discuss. So with this problem here, Bill and Bob are seeing the same photons go at the same speed while they're moving at completely opposite speeds. How does this make sense? It really doesn't. I really encourage you to think about this. Go do some Google research, and it's truly fascinating. One thing I will note is the speed of light, this phenomenon, the second postulate, was from the Michelson-Morley experiment. I apologize if I spell this wrong. How do you spell this? I think it's like this. Morley experiment. And essentially, to sum it up really roughly, they spun a flashlight and some mirrors and some lenses, and they saw which mirror got hit with photons first while they were spinning it, and it was always the same time, which the way they set up this experiment should not be if the speed of light was relative, which it is not. So we'll finish off this pretty long video by talking about a problem we'll discuss in the next video. It is commonly referred to as the train car problem. So here we have 2 flashlights. So this is a train car. Train car. It's moving at some speed v. Okay? We have a flashlight here, and we also have a flashlight here. And this little guy has a button. And this button is wired to both of them. And when he hits it, they're gonna both blink or start shining at him simultaneously, right? But then we have, call it Bob here. I should really use another name other than Bob. And we're gonna call this light is A, this light is B. Now he is also gonna see the same flashlights. Pretend the train car's made of glass. And the question is, does observer 2, which is the stationary guy, or observer 1 see them hit the light simultaneously? So one clicks it, they both flash at the same exact time, but he's moving towards B, but B's moving along with him. And then 2, completely stationary, sees him click the button, flashlights shine simultaneously. Who is going to see him? Well, I'll kind of spoil the answer. It's 2. So 2 sees them simultaneously. But wait, 1 hit them at the same time. And if the speed of light isn't relative, it should hit 1 at the same time for him as well. This is extremely counterintuitive, fairly complex problem, theoretically, when it comes to actually analyzing it. The math is simple, but breaking it down in your head can be pretty difficult. So we're going to discuss why 2 sees them simultaneously and 1 doesn't. And for reference, 1 actually sees the light from B first and then A later, even though he clicked the button. Pretty strange. But, so, next video, we're going to discuss this. Next video. Pretty intro problem to special relativity. Oh, also, I need to note, this is relatively close to C. Obviously, a train car moving at like 50 miles an hour, you're not going to see a difference at all. But this is assuming the train car is moving near the speed of light. But I think that's going to be it for this video. And if you have any questions, feel free to join my Discord in the description. And I really appreciate you watching. And have a great day.